चलो 3.
Three, two, one. Hello everyone. Welcome to our video. My name is Bhavya Modi.
My name is Deepak Kumar.
Myself, Ritu.
So, we, the students of IIT Guwahati Computer Science, are assembled here to explain the topics given by our instructor, Professor John Jones.
In this video, we are going to solve the questions which cover the following titles. We will see about two's complement and overflow in arithmetic operations during two's complement numbers. We will write 3 AC and we will convert it to this machine code for the same 3s.
The first question covers these two titles and the question is as follows. You are implementing a signal processing algorithm that uses 8-bit 2's complement arithmetic. So we are going to convert the decimal numbers into binary numbers in 8 bits and the binary number will be in its 2's complement form. Three data samples need to be processed. X is equal to minus 120, Y is equal to minus 10, Z is equal to minus 80. Your task is to represent these values in the processor's 2's complement binary format and determine which arithmetic operations will trigger overflow flags during execution. And there are three parts to this question, which are x plus y plus z, and x plus z. So, first part of the question will be to convert all the three numbers to its 2's complement form, as we can see here. Decimal to 2's complement. So, let's cover some basics of the conversion. If the given decimal number is positive, then its 2's complement form will be equivalent to its binary representation. If the number is positive, then the most significant bit is 0. The most significant bit is the first bit. For example, plus 100 base 10 is equal to 0, 11, 00, 100 in base 2. And this is in 8 bits form. So 100 can be written as 1 into 10 square plus 0 into 10 to the power 1 plus 0 into 10 to the power 0. And so here you can also see 1100 in a similar format but just in base 2, which will be like 1 into 2 to the power 6 plus 1 into 2 to the power 5 plus 0 plus 0 plus 1 into 2 square plus 0 plus 0. So if the given number is negative, then first take complement of each bit and then add 1 to it. For negative number, the most significant bit is always 1. As for positive, all significant bit is always, the most significant bit is always 0. So when we take its complement, it will become 1. For example, minus 100 in base 10 is 100 in 8 bits form. How is it derived? We can see, we have seen that 100 base 10 is equal to 0, 100 in base 2. Now we are going to take complement of each bit. Now we are getting 100 in base 2. Now we are going to add 1 in the complemented number. Now we are getting 100 in the base 2, which is minus 100 in base 10. Now we are going to convert the given numbers in the quotient to its binary form, which are x is equal to minus 120. Now, first we are going to convert its positive into its binary equivalent, which is plus 120. We can write it as 1 into 2 to the power 6 plus 1 into 2 to the power 5 plus 1 into 2 to the power 4 plus 1 into 2 cube plus 0 plus 0 plus 0. Now, we can also see that uh, we are going to invert the bits. Now, that is the second step. So 0 followed by 4, 1 followed by 3 zeros. Now we are going to invert each bit. It will become 1 followed by 4 0 followed by 111. Now we are going to add 1 to the complemented number. So now it has become 1 000 So now we have got x in its 2's complement form, which is 1 000 Similarly, we have got y and z. Now, the next heading is concept of overflow in arithmetic operation. So firstly, what is concept of overflow? Now, what is overflow and why does overflow occurs? Overflow happens due to limited number of bits. So there is a limit to the number of cases that can be addressed. So we can get wrong output due to the limited number of cases. So the occurrence of the wrong result is the occurrence of overflow. Now we are going to see How can we check the occurrence of overflow in the arithmetic operation? When two 2's complement numbers are added, then if the carry in bit is equal to carry out bit, then there is overflow. But if the carry in bit is not equal to carry out bit, then there is an overflow. When it is equal to carry in bit is equal to carry out bit, then there is no overflow. The exclamation mark followed by equal to denotes not equal to. So we are going to have see the first question, A part, x plus y. Here x is 1 0 0 0 1 0 0 and y is 4 1 0 1 1 0. X plus y is 1 0 0 1 0 0 plus 4 1 0 1 1 0. 0 plus 0 0 0 plus 1 1 0 plus 1 1 1 plus 0 1 0 plus 1 1 0 plus 1 1 0 plus 1 1 1 plus 1 is 1 0 here because we are doing the calculations in binary arithmetic and 2 is represented as 1 0. When we are going to add 3 ones, it will become 1 1. We will see in a later question. So here the carry in and carry out are in the MSB's position. Now while adding the MSBs, the carry that we have got from the previous bits is the carry in, which in this case is 0. And after adding the MSBs and the carry that we get as a resultant is the carry out. So here carry in is equal to 0, carry out is equal to 1. So carry in is not equal to carry out, so overflow occurs. So in the B part, we are going to see it is y plus z. Y is 1 1 1 1 0 1 1 0 in the base 2. Z is 1 0 1 1 0 0 0 0 in the base 2. Y plus z we can see is 0 plus 0 0 1 plus 0 1 1 plus 0 1 0 plus 0 0 1 plus 1 as we have seen before it is 0 1. So 0 and when 1 is in carry. So 1 plus 1 plus 1 it is 1 1. So again 1 is here, 1 is in carry, 1 plus 1 plus 0 is 1 0, 0 is here, 1 is in carry, 1 1 1 is double 1. And here we can see the carry in is 1 and the carry out is also 1. So in this case, carry in is equal to carry out, so overflow doesn't occur. In the C part, x plus z, x is 1 0 0 1 0 0 z is 1 0 1 1 followed by 4 zeros. When we are adding x plus z, it is 0 plus 0 0 0 plus 0 0 0 plus 0 0 1 plus 0 1 0 plus 1 1 0 plus 1 1 0 plus 0 0 1 plus 1 is 1 0. So here we can see the carry in bit is 0 and carry out bit is 1. So carry in is not equal to carry out, thus overflow occurs. Ending the next question to the Deepak Roy.
So now we are going to learn the topic 3 address code. So as the name suggests, what is 3 address code? 3 address code is nothing but it is the intermediate code that is generated by the compiler. So what is the work of compiler? Compiler generates machine code from high level language. It converts the high level language to the machine code for the CPU to understand. So 3 address code, it is an intermediate code generated by intermediate code generator in the compiler. So it is just a type of representation of the expression given by us. Now moving forward to question number 2. Here it is written, you are given the following grammar for arithmetic expressions. So we have to remember this, that a compiler has a specific grammar. So every compiler has a specific grammar. So the question has to specify what is the grammar is defined for the specific compiler. Like here the grammar is S is equal to F equal to E implies E plus T, E minus T and T implies T into F and F implies E, A, B, C, D. Now we have to consider the assignment statement, that is A equal to B minus C into B plus C. We have to remember uh, that the given assignment should be in correct form. It should be in like B minus C into B plus C. It shouldn't be like B plus C into B minus B. It is a lot of change. Like it shouldn't be like C minus B into B plus C. Otherwise, the whole number will get reversed. Now, seeing forward, we have to construct the 3 address code using temporary variable. We are using three temporary variables here, T1, T2, T3, to store the values and then multiply and then to store back in the original one. Like we are assigning T1 equal to B minus C and T2 equal to B plus C. Here the order is important. T1 can't be C minus B. You have to remember that. And T2 can't be C plus B. Like here T3 equal to T1 into T2. We can't write here T2 into T1 as the expression should be exact same. Now T1 equal to B minus C, T2 equal to B plus C, T3 is T1 into T2. That implies that T3 is B minus C into B plus C. And then we are assigning the value to A. Then A becomes B minus C into B plus C. We have done the three address code now. Now assigning the next topic to my friend Rituraj.
So now in the second part of this question, we need to generate a RISC machine code for the three address code that we obtained in the first part of this question. We are given several operations like load, store, add, sub, and mul instruction. Each data movement instruction, that is load and store, they will have one memory operand and one register operand. And while the arithmetic operations will have three register operands. Now, all these things like load, R1, B, C, all will be stored as a bit format in machines. Machine will have a certain bit length for each of the instructions. But we can see load R1B. This means that the value of B will be loaded to a new register, R1. As we load the value of B and C into R1 and R2 respectively, we can now use those registers for the arithmetic operations as they don't take memory value, they take register values. So after loading the values of B and C into registers, we will perform the sub operation, like sub R3, R1, R2. In this, we are storing the value of R1 minus R2 into a new register operand R2. Now the value of B minus C will be stored in R3. Similarly, when we perform the add operation, the value of R1 plus R2 will be performed in R4. The order is necessary for both of the operations as if we change the order like sub R3, R2, R1. Then the value of R2 minus R1 will be stored in R3 rather than the value of R1 minus R2. So that will change the question completely. So after storing the value of sub and add in R3 and R4, we now need to multiply both of those to get B minus C into B plus C. So we will write mul R5, R3, R4. It will be like R5 will store the value of R3 into R4. So we have a register R5 which contains R3 into R4, that is B minus C into B plus C. But our desired question was A equal to B minus C into B plus C. So now we have the value of B minus C into B plus C in a register named R5. Now we need to move it to a memory operand, that is A. So we will use the store instruction, which suggests that if we write store A R5, the value which is stored in R5 will be given to the memory operand A. And this will be this machine code for the 3AC that we have obtained above for B minus C into B plus C. Thank you.
So thank you for your presence. I hope this video will be helpful to you.